All right, we're going to continue. So many students struggle. Failure, especially when you're learning something new, can reduce self-efficacy and lead to more people dropping out or quitting. But practice is crucial for learning. So you have to practice, but that practice must be successful. So if you're unsuccessful, that can reduce self-efficacy. And it should include timely feedback. And then Mickey Chi's framework, ICAP framework, says that interactive practice or work is better than constructive, where you're creating things, or active, where you're just moving something or doing something active, versus passive. And we know that from a lot of research that active learning is better than passive, but even beyond that, interactive, particularly communication between you and a more knowledgeable other, can improve learning. Space practice is better for long-term learning, even though students like to cram right before an exam. We know that for long-term learning, spacing out your practice is better, but that's a form of desirable difficulty, which are things that slow down initial learning, but improve long-term learning. And cognitive load theory is one of the things I most draw on. And humans process new information in working memory, and we have unlimited long-term memory, but we have to bring everything into working memory to work with it, but it's limited. You can chunk things to make them smaller. So once you know something like a dance move, if I ask you to do that dance move and you think of it as one thing, even though it's 20 different pieces, now it's one chunk. So what we need to do is to try to create practice systems for people so that they can learn, so they can chunk information, they can store it into their schemas and long-term memory. But one of the ways we can do that is we often give people whole tasks or make people write code from scratch in programming, which is a complete task, which is authentic. You have to write code, but it can overwhelm beginners. And so in that case, a completion task where they don't have to write everything from scratch could help reduce cognitive load. And one of the things that's been very effective based on cognitive load theory is worked examples plus practice. We know that just giving people practice problems and asking them to do that isn't as effective as worked examples, seeing expert solutions to problems, plus practice that sort of makes you pay attention to those worked examples. People don't always learn from worked examples unless they actively cognitively engage with them. Well, the other thing to watch out for, though, is expertise reversal effect. And that's things that we do to help beginners can irritate experts and get annoying. So one of the things you want to do when you're helping beginners is have scaffolding that fades. So over you develop expertise, the scaffolding or the amount of help that you get should be reduced. So one of the things I've been studying now for a long time is Parsons problems, named for Dale Parsons and Patricia Hayden, that first published about these. And the idea is it's a completion problem. So instead of making you write code from scratch, we give you all the correct code to solve a problem. We mix it up. We have pairs of correct and correct code. You can see here the purple edges with an or. So to get you to pay attention to what's the difference between these two, one of them is correct. And then you just drag the correct blocks in order, but also with correct indentation in Python. These usually have lower cognitive load than making people write code from scratch. Students perceive them as easier than writing code from scratch. And there's many variants of this now. One of the variants that I created were adaptive Parsons problems. So I first put Parsons problem in an interactive ebook. One of the things I've also been doing is creating free and interactive ebooks so that people have lots of practice and immediate feedback. And one of the things I found is that even for basic Parsons problems with a few blocks, some students really struggle to solve them, taking hundreds of attempts to solve them when there's like 5 blocks. Like, how are you taking 100 attempts to solve it? And some people never solved it. So then I created 2 kinds of adaptations. So if on a problem you're having problems, if during solving this problem you're having difficulty, you can click on this help button and it'll help you. And I'm going to stop sharing this and switch to a different. So let me share that one. Okay. Where's the desktop here? Just that. Okay. That's going to be a little bit. But I didn't see this. Oh, something moved. Okay, that's why. Just one second. I had it open to what I wanted, but now it's moved. This is one of our free interactive ebooks. So this is one of our Parsons problems or mix-up code problems. Oh, next one. So you can, and we have these pairs of correct and incorrect code. You can just drag things over as I've done, but I'm gonna make mistakes to show you how this works. So if I'm trying to get a solution and I make at least 3 incorrect attempts, it'll tell me that I can use the help button to make things easier. If I did use any of the wrong blocks, these distractor blocks, it animates going back and repairs with the correct to say, hey, try that one. And then if I keep asking for help, it'll start combining blocks, starting with the ones that are furthest apart. And it'll do that till I get down to 3 blocks. And then it'll tell me, hey, you should be able to do 3 blocks. In fact, I'm already in order. So, and then I just have to indent this. So that's the adaptation to help people get to a correct solution. Back to PowerPoint. Zoom.
I think you're okay.
It's okay because I already said it.
No. Just stay sharing the desktop, and then when you switch, it doesn't matter.
Yeah. Okay. Good. Sometimes I find that gets a bit. Okay. So that's one type of adaptation. The other is between problem adaptation. So how you done the last problem can affect the difficulty of the next problem. So if you solved it very easily, we'll make the next one harder. We won't show these pairs of correct and distractor blocks. We'll just randomly mix the distractors in. And if you had difficulty, then maybe we'll remove some of the distractors and pair the rest with the correct code. I've also have a PhD student who's working on microparsons. So most Parsons problems, you try to put a whole bunch of blocks of code into a vertical order, perhaps with horizontal indentation. She's also been working on smaller than that. How do I put things into a single statement? So we've been doing SQL, regex, Java, public static void main, it's forever. So we've been working on that as well. So our research on Parsons problems, and there's a paper at the bottom of that, that is an ITSE working group that I led that did a nice overview of the literature. So most students find them useful. Over 75% usually say they're useful for learning. They're usually significantly faster to solve than writing the equivalent code, with similar learning gains from pre to post test. There's simply more learners complete them versus write code problems when we have voluntary practice. So we've done some large MOOC studies where people voluntarily joined a practice thing and the people in the right condition versus Parsons condition. We dropped a lot more people in the right condition. They give up. They can be used to learn common algorithms. They're also used for exams. They usually correlate nicely with write code. And nearly twice as many people are likely to correctly solve the adaptive than non-adaptive. However, there's some problems with Parsons problems. One is that some learners are like, I don't want to solve that. I'd rather write the code, especially if the Parsons solution doesn't match what they were thinking of doing. And then some people can solve them because the adaptation, the help, can get them to a correct solution, but they don't understand the answer. So one of the things we've been doing is giving students a choice. Great, it's scaffolding. If you don't need the scaffolding, it should go away. So if I give you a Parsons problem as practice, we now have a toggle feature where you can switch to the right code problem and solve that instead. So fine. We also, though, if you're writing code and you're stuck, we can pop up a Parsons problem to help you. We don't let you switch to it because that's easier, but it is a form of help now. And we've done studies on that. We initially did a Think Loud study with 11 students. We found that they popped up the Parsons problem to get started when they read the English description and had no idea what was going to be in the solution. So they would kind of look at it to get a sense of what's in the solution. They would also do it when they were stuck on a particular Python thing. How do I do that in Python? Oh, well, pop up the Parsons problem. It's got to be there. Or when they finished writing code and didn't pass the unit test, so they use it to debug. What's different in this Parsons than in my code? They didn't necessarily even solve the Parsons problem. They just used it as a directed search. Then we also did a between subject study with 81 undergrad students, and the people in the Parsons group took significantly less time to complete the practice problems. However, when we tested pre-post, there was our ceiling effect on the pre-test. So we ran another study with 89 undergrads, and we had Parsons as scaffolding versus no scaffolding. And particularly students with the low computing self-efficacy, we did a pre-test that talked about self-efficacy. With scaffolding, people in the Parsons as scaffolding group had significantly higher practice performance and practice efficiency than the no scaffolding. But we still had students who didn't understand the Parsons solution. They could get to a correct solution, but not understand it. And they didn't find the Parsons problem as helpful if it didn't match their approach. So particularly when LLMs came out, I said, this is fun. Let's try using these to create personalized Parsons problem. So if you started writing incorrect code, can we use the LLM to find the closest correct solution and serve that to you as a personalized Parsons problem? So that's what we've done. We first did a technical evaluation. We took a bunch of student code, checked to see is that solution that's generated by an LLM closer than the general, most common student solution? And in fact, it was. And then we did a within subject study, Think Loud, with 18 students, undergrads, and they went back and forth between both this generalized solution, this generated LLM generated solution, that we just give them the solution and they could use it, versus solving a personalized Parsons problem. So the way this looks is there's a write code problem on the left-hand side. There's a button, the help button, and it'll generate, it'll tell them to wait because it takes a little bit of time to generate a personalized solution. And then it'll pop up the Parsons problems. We're also doing something different here that we haven't been doing, where anything you have correct, we're putting as static. You can't move it. You already have that correct. So it's also localizing the issues. And then any of your incorrect code, we're using as distractors. So if you made incorrect code, that becomes the distractors. So now they're like, wait a minute, why is my code mixed with something else? As a possibility, then they have to think about, oh, maybe my code's not right. So there's two options here. One is if they pop it up right away and they haven't really written anything or hardly anything, then we go ahead and serve them a Parsons problems made from the most common student solution. So, and with usual. But if they have written things, then we use their incorrect code to create the distractors. So modify things. They can, when they want to get help, they just click this help button and it tells them loading help. You're achieving a little bit of motivational, you're capable of achieving great things. We can help you get there to get them to wait. So far, the students' feedback was, okay, it takes a little bit of time, but they were still busy looking at the problem. So they didn't feel like it was wasted time. So the generation process is we take your incorrect code. We also pass into the LLM problem description, a representative student common solution, an example incorrect student code, and the corresponding verified personalized fixed code. And we get a pre-written fixed code query template to the LLM. We generate the fixed code prompt. We pre-process the fixed code. We may have to revise the prompt based on if there's a failure, if it doesn't do the correct, and we have the unit test, so we can tell whether it's correct or not. So we can test with the unit test to see if it worked. We do 3 different attempts. If it doesn't work after 3 attempts, we go back to the common solution again. So we try to get the closest correct solution. So we check the unit test for those, we check the closeness, and we generate this personalized Parsons problem. So the results so far is we're calling this active hint. It generates Parsons problems that are significantly closer to the student's incorrect code versus the most common student solution. Most students prefer receiving a personalized Parsons problem versus the correct code. So they had 2 options. You know, we did 2 different within subject study, but with 2 different conditions back and forth. And they could either get the personalized Parsons or just here's the code from ChatGPT and they could just use it. Most people said that they preferred getting the personalized Parsons problems. Some still could solve the Parsons problem, but not really understand the code. So we still need an explanation. And we're doing a classroom test in January of personalized Parsons versus generated code. Future work, we want to create fully adaptable Parsons problems. So one of the things we found, right, is students would pop up a Parsons problem when they had just read the English description because they didn't know how to get started. So what we want to do instead is to pop up sub-goal labels then, and then hierarchy of sub-goal labels. And then you can expand the sub-goal labels if you don't understand how to break that sub-goal label into smaller parts until you get down to the code level. Once you're down to the code level, you can either write that code or you could use a micro Parsons to help you. And so we're thinking this full level. Plus, we also want to have full level explanations, anywhere from a high level explanation to a line by line explanation to a character explanation. What does this character do? What does this piece of a line do? We want to generate the personalized micro Parsons for each sub goal. And then we want to try these in other fields too. So we've been using them in programming, but there are like proof blocks that are used in math for discrete math. And we think this would be very interesting in math or in other fields to use this. It doesn't have to be programming. So my recommendations are that people try to create tools that leverage LLMs. So we're leveraging existing student data to create what's the most common student solution so far. Create personalized practice with different levels of explanations where you guarantee the correct solution. So guardrails so that students don't just use LLMs and have no idea if the answer is correct or not. And then what I think the real tricky part is how do we get students from over relying on this? We know that if they just take a prompt and put it in ChatGPT and they paste the answer and no learning occurred. So how do we get them to actually think about that solution? Use LLMs when they're stuck or when they need help, but don't just copy paste stuff and expect to know anything. And then how do we keep students in the zone of proximal development, which is where they're challenged and they learn the most, but they're not frustrated and give up. So I think those are some of the issues that we're trying to solve. I'll end a little early. So take questions.